Thank you. In my today's lecture, I will start from kind of correction from my yesterday's lecture. Thank you, Professor, for giving me the view so that I can see my error there. But the problem was there. I defined from R to R. No, it is always that this is context differentiable at zero. It is always, but when we manipulate case that this fails to be Fenchel differentiable, so I cannot find the sequence, but the one which I have shown, one of the n. So this is an example from my yesterday's lecture, which I showed that this is context differentiable. That's obvious. But it says that it fails to satisfy Fenchel differentiability. But the fact that it might not be true that it fails to satisfy the Fenchel differentiability. So the simplest way which I found that simplest way supporting statement so that we found that certain functions fail to satisfy Fenchel differentiability. I would like to state this term. If this function is differentiable, Fenchel differentiable at the point x0, then f is continuous at x0. So we can take this as one test, but no exception. If it fails that the function is not continuous at x0, it is not a Fenchel differential. So we can use this. So I would like to give a very good example, an improved version of my previous. F of x1, x2 is x1 over the power 4, x2 over x1 power 6 plus x2 cubed. If x1 the power of 6 is different from the negative of x2 squared, x2 cubed. This denominator is non-zero. Zero otherwise. So let's test this for the 0 point. So here, f of 0 plus ph minus 0 over t equals to f of th t, which is obviously h1 to the power 4, h2 over, right? We have square here to the power 3, h1 to the power 6 plus h2 to the power 3. If this denominator is 0, different from 0. If h1 6 is different from this one. But if h is 0, so this Its limit is 0. That's true. For all h. So this implies that the zero operator is a Getachew derivative. The zero operator is a Getachew derivative. So this implies that f is dependent. At zero with Getachew derivative. Getachew derivative of f as 0 to be at 0. But not that the Getachew, the Getachew derivative in the Fenchel derivative are unique. That's obvious. They are unique. But how we can show that? This first to be not Fenchel differential. It is true that or if I make this H1 is H2 is equals to H1 to the power of 2, then what will come is f of sorry, this is x2. If x2 this value, then f of x1, x2 gives us 1 over 2. Noting this, this function is path dependent. Path dependent. This always that it is path dependent. So the limit doesn't exist. The limit doesn't exist. So you can see that f is not continuous at 0. F is not continuous. It's path dependent. So if f is not continuous, like this theorem, you can show that f is not Fenchel differential at 0. It's not Fenchel differential at 0. This is, I think, a very good example shows that f is context differentiable, but not Fenchel differential. It's not Fenchel differential. If we use indirect competition form of the Fenchel differentiability, we can use a sequence. I think this will not make an effect, because now for this sequence, this is valued to 0. But for that indirect competition of Fenchel cannot be 0 for a linear operator. We cannot find a linear operator for this. Just find a sequence which converges to 0, so that the first and the second coordinates have kind of this relation. It's first here. So take this as my correction. That I think this is a good example. Now let's come to my today's discussion, which I left yesterday, the subdifferential. The subdifferential. I will define this in a normal space. My discussion is actually always in a normal space, unless otherwise I stated x. If I am not stating x is or a space is a normal space, take it that way. Let let me state it here, X be a normal space and F is given be a function. Then the sub-differential of F is denoted by this is a set valued mapping. It is a set valued mapping. What kind of set valued mapping? A set valued mapping from X to the power set of its dual. That is from X to the power set of the dual space of X, given by the term differential of F at a point X in X is the set of linear functionals. Found the linear functionals, say the element in the dual space, says that y minus x at x star, this value, this real value is less than or equals to f of y minus f of x for all x in x. This is a self-differential. Definition of self-differential. Sorry, y. All y an element of x. This is a normal self-differential. We have also e self-differential. Self-differentiability has Clark. We have self-differential. This is a normal self-differential. E self-differential is plus e if you have e. But let me concentrate here. This is very important for me here. But if you stretch this concept, this has a lot of self-differential calculus, a lot of concepts here. So this is what we have. Note that here. If value of the function is positive infinite, then assuming that if the value of the function is positive infinite, assuming that the domain of f is non-empty, if the domain of f is non-empty, this is some differential of f at this point x is implicit set. It will be implicit set. And for this set valued mapping, the domain is defined by this. The domain of the self-differential is the set of x in the space x, and that the self-differential of matrix is different from empty sets. The set of points next with the self-differential is not empty set, it's the domain of f. So being and then empty differential at the point is very important with regard to the extended version of self-differential in optimization. So what is the link between the basics of Getachew differentiability, Getachew derivative, and the self-differential? And the self-differential. If f of x is convex function, and latex differentiable. Latex, then the subdifferential is nothing. It's just singleton. It's just singleton. That is the latex derivative. If f is a convex function, then it is latex differential at the point x. The subdifferential is singleton. That singleton point is the latex derivative. That is the latex derivative. So f is convex, and latex. Benjamin? Yes. So let's take arbitrary point in the subdifferential. Took an arbitrary point in the subdifferential. If we can show that this point is equals to this latex derivative, meaning that every point is equals to this one, the latex is unique, meaning that it is singleton. Latex derivative is unique. So what we need to show is this point equals to this one. So this implies that x star y, if this value is 1, x all x. So I can, this implies that for t greater than 0, we have x star x plus ty minus x. This is for all y is less than or equals to f of x plus th. So this is h. This is th minus f of x. All this room. This is direct consequence from here. Then in that, from this we have here we have t. This is concept. This is less than or equals to f of x plus th minus over t rho h in x. So taking limit, right? It's t goes to 0. This is obviously the latex derivative of f, meaning that the directional derivative of f at x in the direction of h. That is, because I like this representation. All next. Now, if we compute this again for minus of h, this is greater than or equal to this one. So we have this star. So if you compare this implies that so this gives us that for all H. So this the mark is like the star. From star and double star. We have convex derivative H. All H in X. Is for all H in X. An example, X star. First term. Since X star is arbitrary, this is that all this equality is on X, right? Because this is linear functional, this is linear functional, this on X. The properties, equality is on X. On and this is unique. This property gives us a straightforward. The differential of f at X, this will force us to have all of this. Only this equality is these operators, these operators, this equalities is functional value of X. They are having same function. And this is unique. This is unique. So from unique value, if we have, anyways, this concept will force us to have the sub-differential to be unique. Differential of this function context to be unique. So now we can go to the first order condition with regard to sub-differential. That is a very simple concept. Function, then x bar is minimizer of f, global minimizer of f, if and only if 0 is an element of the sub-differential of f. This is direct only to proof. This is direct. This is the first order condition of existence of duality condition. We don't need to show this. We don't need to show this direct by the definition of this one, definition of this one. This is straight. So to go to the property of the sub-differential, meaning the sub-differential calculus, I would like to have the following definition. Let's X and Y be normal spaces. And this is an operator. They are an operator. They are mappings. Given this. So this operator A has a joint operator. Then A has a joint operator If exists, even it might not exist. It might not exist. Denoted by S star. This is if exists, might not exist. A has a joint operator if such an operator exists. As an operator denoted by this one, and S star is given by S star. This mapping should map from the dual of y, y to the dual of x. It should map like this, such that it's not only this. The S star of y star should be equals to y star of A for all y star in y star. An operator has an adjoint operator if such exists, if such S star is mapped from y star to x star, so that it should satisfy this. What does this mean? This means the S star of y star of x, this value is equals to y star of A of x for all x in x and y star an element. So it should operate this way. It should operate this way. But this is true. An operator of this form has an adjoint operator. This operator is bounded in the operator. It's bounded linear operator. Bound continuous test pattern. If there is linearity, continuity, and boundedness are the same. Continuous is also the same. Continuous linear operator, bounded linear operator for mapping to mapping, they're equivalent if linearity is there. Linearity is there. Is a bounded linear operator, then the adjoint operator exists. Adjoint operator of any exists. And what is a very beautiful property of the adjoint operator? The adjoint operator of A exists. So what? But the norm of the adjoint operator, this norm of adjoint operator is in the norm defined from y star to x star. It depends on form of space defined by this one. And exactly this is equals to, this is actually the supreme morph. And the space on this is over in y star, where y star This is deficient. And this is the supremum, this one. This is strength. X in X, which is in Y, which is introduced in Y, introduced in X, 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 different concepts. The supremum is obtained over this unit, closed unit. This is it. On the boundary also. The supremum is then at the boundary, you can make it expansion. But this is the dual of the dual in this node. Equals to of y star of y, right? But we cannot because it is linear functional. This is enough. Because y star is real valued, absolute value. Y is y, and it's different from it. So amazingly, if the function is bounded, linear with the mapping is bounded in operator, the joint existence is a joint satisfying this. So why I did this is I will discuss about the subdifferential calculus. Subdifferential calculus. That is, what will be the subdifferential of the sum of the functions? The function. Let x and y be normal responses. Let x and y be normal spaces. So what are the properties of the subdifferential? One, if f from x is convex function, for alpha greater than 0, the subdifferential of alpha of f of x upon x next. How about the sum? If we have two functions operating on the same space, what is the subdifferential of their sum? If it is f and g, let's have to. If f and g are convex functions, then the subdifferential of f at x, that is the subdifferential of g at x. And that's it, the subdifferential or x in x, or x next. Equality preserved under two conditions. this or this are equal if FLGR proper, the function convex and the no semicontinuous functions. And also, if this is satisfied, this is very important. The interior of domain of F intersection domain of G is nullity. If these two conditions are satisfied, then equality preserved. The sub-definition of X and the sub-definition equals the sub-definition. When showing this, when showing this property has a very important impact. It's very important. This condition is very important. The third one, about if it involves a linear operator. If F is from Y R is convex function, and A is this is continuous linear operator or bounded linear operator. It's bounded linear operator. Then the following holds. Then S star of the sub-differential of F at Kx, if maps to this one, this one. This is a subset of the sub-differential of the composite. This holds. This has a very important properties. Sub-differential. Actually, if we have, you can combine here. Must be mind. Often maybe we come to conjugate one of this. We my first time with this. So if this is satisfied, if this has a solution, my first order duality condition, zero is a sub-differential of this one. We have this one. Anyways, we can stretch this one. We can stretch this one, combining it with this and this one. Now, I will like to state the Tucker condition, complicated part of optimality condition, version of optimality condition. That is let X be a normal space. I don't need to state actually. Let X be a normal space. And because and it is C in the subset of closed convex subset of X. Let X be a normal space. C is closed convex subset of X. And is proper convex and non-semicontinuous function. With this condition, I want to have this condition. With interior of C intersection domain of F is non-empty. Then X bar is the solution of the minimizer solution. The solution of the infimum of the constrained optimization problem. So meaning that it's always that X bar is in C. That's always X bar is in C. If and only if there exists a linear functional, bound linear functional, such that this star is an element of the sub-differential of F at X bar, and minus of this star is an element of the normal cone of C. This is a very beautiful optimality condition. So this is the solution of this one. This point is the solution of this one. If you know if you can find a linear functional, found a linear functional, an element of the dual space. These are an element of its dual, the dual of X. So that these two conditions are satisfied. So if I would like to use this with a specific KKT condition, this is a version of KKT condition under a condition that F is Gatex differential, and the condition that F is Gatex differential. And this is analogous to the Slater condition. Slater's meaning that the constraint qualification. It's analogous to that kind of concept. It's analogous to that kind of concept. The proof is very easy. Very easy. Meaning that I will go straight by if and only if I think X is minimizer of X, meaning that let's have this. You see, meaning that I can make this with this as the indicator function of X, so that I can make this unconstrained optimization. So I can make it unconstrained, where the indicator 0, X in C, infinite otherwise. So if this point is a solution of this one by first order optimality condition, differential, differential, This is true if and only if 0 is an element of the subdifferential of f plus the indicator function of c, the indicator function of c of x bar. Indicator function on x bar. So this is equal to the subdifferential of f at x bar plus the subdifferential of the indicator function at x bar because of this condition. So the interior, the domain of this one is the domain of the indicator function is C. So there is only the subdifferential x bar, subdifferential of the indicator function. If you want, there is Z star, an element of minimization. This means star is the subdifferential of x bar, and it must be one element from here. There's some is to zero. So one is the negative of the other. So meaning that this one. That's true. This line is the differential of excellent. If you want to manipulate this, maybe if you do not think, I don't think it's necessary to write it there. What on y in x? So if y is out of C, this will be infinite. So this implies that this is binomial. Should be in C. So if it is C1, this is obviously in C. 0. So this is the normal cone of C at x bar. This is the norm. So this is this cone. These are elements of differential. And we have subdifferential, right? Subdifferential of the indicator. Subdifferential. If this is an element of subdifferential, then this is an element of normal. This is normal. Normal cone of C at x. C at x. So it is here. Now we're going to see kind of way to extend subdifferential with it is with French English. So I would like to discuss the following. Fenchel duality, call it the Fenchel duality. Next the normal space. And f is from x a function. Then sometimes they call it Fenchel conjugate, Fenchel transformation, or Lagrange Fenchel transformation, Lagrange Fenchel. Dual, the Fenchel conjugate of f denoted by f star is mapping star of set of points in the dual space x into this. Where this mapping is given by is a mapping given by f star of nonlinear function is the supremum of x and x star minus f of x. Where this supremum is 10 over x. This is the Fenchel conjugate of the function. Call it the Fenchel conjugate of the function. The Lagrange Fenchel conjugate of the function. This has a very important problem with discussing primal dual. Primal problem is a view of it is dual problem. So this Fenchel conjugate of a function is well defined because since to make it well defined, it be should make here proper. Proper function. Meaning that the domain is nullity. Proper should be proper. This is a proper function. So the domain is nullity. If the domain is nullity, we say this. Then it is obvious. Just this thing cannot be negative infinite. Cannot be negative infinite. So this mapping it's the point from here to here. So it's well defined and exact. It is well defined. Star is well defined. Let's define space here. Define space here. Now let's see examples. Examples of plot. X is a normal space. So example 1, A. Let's have a function f. F of x is equals to x naught star of x must be for x naught star is an element of the dual space and P is an element of R. Since it's dual, so F is really valid function. What will be kind of the dual of a kind of this function? So here, the star of arbitrary point in the dual is equal to the suprimal. This one, by definition, replicate. This gives us directly x star minus x naught star of x minus b. Actually, this is zero. If it happens that this is zero, it will be minus b. If x star is x star is equal to x naught star. If it's not happening, this value will be infinite. So meaning that this can be written as this dual is the indicator function on minus b. Which is equal to no. Minus b. This dual is this is equal to this one. So this function, the dual is that. And actually, we can have show. If this is a function, then it is dualist, or 1 is an equal to 3 is infinite. Then the dual of this if star of star is 1 over q norm of x star. This one is in the dual q. If 1 is less than p, less than infinite. If p is equal to 1, then it is the indicator function over the unit closed ball, the dual space. So what is p? What is q? Here is q is a conjugate of p. B star is the unit closed ball in the dual space. Let me write it here, where the value of q, the value, so that it gives you this. they start with the unit clock level. In the Y-star space. Unit clock level. Unit clock pole in the dual space. And this is an indicator function. Indicator function. So if the space is Hilbert space, if finite dimensional space, it will be self-conjugate if p is equals to 2, right? If p is equals to 2, it will be self-conjugate. So the function itself is a conjugate of itself. Function is the conjugate of the function is itself. If it is finite dimensional, for p is equals to 2, then we call it self conjugate. So the third one, maybe what will be the, if this Getachew differentiable, the Getachew derivative is boundary linear operator. And boundary linear operator is x to r. That's the Getachew derivative. What is the Fenchel dual of the Getachew derivative? Is an x differential, convex and Getachew differential. I need convexity here. And Getachew differential let this be convex and Getachew differentiable function. So if it is Getachew differentiable, meaning that the Getachew derivative of f Getachew differentiable at a point. Let's see. Let's make it at a point. We need it. We need to test it at a single point. That is Getachew differentiable at a certain point. So this is the Getachew derivative of f at x. This is the linear function, right? It's the Getachew derivative. But what is the Fenchel conjugate? The Fenchel conjugate of this Getachew derivative, right? What is h? What will be this? Very exact. A certain maybe. This is a bounded linear function, right? It's a bounded linear function. What will be this? Getachew derivative of f. This is you can make a problem just to make it close with this one. Or not to mess it. By the definition, you get this. So this is equal to the supremum of x star h minus the limit of f of x plus th minus f of x th x over t as t goes to 0. But note that this limit can be computed. This limit is equal to, since f is convex, by simple computation, we can show that phi of from Moreau infinite are given by this one. We can show that this is increasing function. Very easy to show this. It's very easy to show. This is an increasing function. If it is increasing, the limit as t goes to 0 means that the limit is the infimum over t over this value is this. If it is convex, this limit can be found by this one. Since it is increasing function. So it means that this supremum h next supremum t here equals x plus h plus f of x over t because of this negative supremum. So I can interchange. This is possible. Super over x, super over y, if we interchange, no problem. Super if we can interchange the infimum over x and the supremum over y is greater than or equal to the supremum over y, the infimum over x. But if we interchange this, it will not be equal. This inequality is preserved. Infimum and supremum can interchange. So I can interchange, so the equality is preserved. So this is, if I make it the supremum, if I make this Z, if this is Z, this becomes this one. TH becomes Z minus X minus F of Z plus F of X over T. Where this supremum is completed, the running over the whole space. X star into Z, 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 X minus plus F of X, then we have minus X star of X over T. These are independent of Z. So this implies that. So the dual of the matrix derivative. Matrix derivative for a real valued function, for a real valued function is completed. This means that it's completed. The one of the derivative of X, X bar. The Fenchel conjugate of the convex derivative this this value is Fenchel conjugate at F. So this is the dual, the French conjugate of the convex derivative. The convex derivative. So the convex, we have the convex derivative. For this convex derivative, it is French. It is Fenchel conjugate. Fenchel conjugate. Equivalent conjugate using this. Using this one. So these are the examples. Now let's come to properties of the Fenchel conjugate. Fenchel conjugate. X, F, G, F1, 2, then the normal space. The proper functions. Do I need convexity? I don't need it. The Fenchel conjugate, we need one for the function to be portable. Convexity is not necessary. Convexity is necessary. It's enough that we have a proper function we can define. Then this is on this. F is less than or equals to G. This implies that F star is less than or equals to G star. With the definition. So the infimum of Fi runs from 1 to n. The Fenchel conjugate of this one is equal to the supremum of each of the Fenchel conjugate of each function. This is this preserves equality. But in case of this, how is this? This works. These are very important properties of the Fenchel conjugate. This is quality is preserved. This is less than worse. Now I have a very interesting theorem. That is, if f is proper function, if f is proper and convex function, let's make it let x be proper and convex function. Then x star is an element of the subdifferential of f at x if and only if the Fenchel conjugate of the of f at x bar is simply this. Simply the supremum is attained at this point. If x is an element of the differential of f at x, then this whole is this one. Anyways, if this is true, this means that the self-differential of x is the set of all points in the dual space, such that points which satisfy this condition is this one. So the definition of differential would be this. If this is the relation between the differential and the Fenchel conjugate. In this way, suppose x star is an element of the subdifferential f at x. If it is the subdifferential of f at x, so this means that this implies that x star y minus x is less than or equal to f of y minus f of x. All x. This implies that x star y, the spring here, f of y less than or equals to the spring, this difference here minus f of x all x. So if we take supremum, taking sup both sides, right? For all y squared. We simplify the supremum of y runs in y, in x. Y runs in x is less than or equals to what it means. But this is the conjugate. This with my definition, what we have is by definition. If you start, right, 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 six. But this is greater than or equals to, this is greater than by definition. This is greater than because any arbitrary point replaces in one. Here. Okay. Okay. So by definition, we have this implies. So from this, yeah, this. So this is Prof for the reverse. This is very simple. X. Then by definition, X star, we have um, F star of X star is a supremum which is greater than or equals to this is true. All supremum is greater. So if we combine these two, it will give us directly subdifferential equation. Combine these two, because this is this one, this is this one, this is this one. If we rearrange this, all y or x so this is very important reason the point of view of functional analysis. It's a very beautiful result. Now, having discussing about this, on the left is the topic, which is a biconjugate. Biconjugate. About the conjugate of the conjugate. What happens? Conjugate function, then it is conjugate. But I would like to remind this, I would like to express this in the sense that for each x, if we have a normal space x, if we have a normal space x, and it's dual in this one, then consider the dual of the plus. The dual of the dual space of dual. So for each x, next, I define this x of x star, which x in x, meaning that if I define it this way, for each x from x star to r by x of x star is meaning that each point in x represents a function, a boundary linear function on the dual space of x star. Okay, on the dual space of x star. We have this competition, this is really good. Anyways, this is clear. Although this, in the sense of this one, x is a subset of the double dual. The dual of x of dual. I can have kind of this condition so that each element in x can act as a boundary linear function on the dual space. Dual space. So meaning that space x can be considered as subset of this double dual. Okay. So if x is equal to x, if all boundary linear functions can have, if x is equal to x double dual, we call it reflexive of the space. But with this weak condition, this is true. This is true in the sense that each x is operating this way. This is true. Now, I will try to define the conjugate of the biconjugate function. I mean this one. Let's x be a normal space. I should take the proper function. That's enough. We need only function to be proper. Then by conjugate one, by conjugate of f is by conjugate the by conjugate in this one, we expect to have the definition of this one. But we define if it is reflexive, that's okay. It's reflexive, that's okay. There's a biconjugate dual. The biconjugate of a function f denoted by f double star is, so this, the biconjugate is a restriction of the Fenchel, the Fenchel conjugate of f star on x. It is a restriction. The biconjugate we expect to be defined of the whole space x double dual. So just to discuss several problems, since we have several reflexive spaces, so the biconjugate is defined as the biconjugate of f is the restriction of the Fenchel conjugate. The Fenchel conjugate. The Fenchel conjugate of x star on this one, given by the restriction of this one, it's only x. Okay? The biconjugate function, the biconjugate of the function is the restriction of the Fenchel conjugate of this. If we consider the Fenchel conjugate, should be its double dual. So as a definition, is supposed to consider all spaces, so that this is the biconjugate dual on this restriction of the space x. The space x. So what is a biconjugate? Means here. The biconjugate, the Fenchel biconjugate is this. Star of star of x is equal to the supremum of x star. This means, by definition, this is the supremum of x star of x minus y. When y runs in x, by definition of conjugate, we have this one. But this is neither or equals to. This is greater than or equals to at a point x, right? So this implies that if the biconjugate is less than or equals to the function f. The biconjugate is less than or equals. But equality is preserved if we have an additional condition, convex and logically continuous. Convex and logically continuous, then F. So to end our first lecture, our step one, very important term, very interesting term. Let F from the normal space X the proper and convex function. See the following is one. If X is reflexive normal space, then X star is an element of the self-differential if X implies X is an element of the self-differential if star exists. X is reflexive and F is again your semicontinuous. In this condition, then X star is an element of the self-differential of X. If and only if, or if and only if X is an element of the self-differential. This proof of this one is very easy.